Hello. Okay. All right. So we're not going to be having a mic today. So just let me know if you can't hear me in the back. Am I good at this volume? Yeah. So we're going to be teaching y'all about computer vision today. And I just passed out some papers because I want y'all to work through some problem I have. All right. Okay, so today we're going to be talking about computer vision and a bit of an overview of where we're at in the ML Monday workshops. I'll just go over that real quick. So we've done introduction to ML Monday, introduction to deep learning, transfer learning, and deploying models. So just congratulations for all of y'all who stuck along this long. So, yes, thank you. So we basically finished the first half of ML Mondays, which was introducing y'all to the basics, and now we're gonna go more into applications while also teaching y'all about more specific techniques and probably more in depth. One caveat is from last week's experience. I think we're gonna be doing two workshops, one for more coding focused workshops and one for more conceptual and introducing the ideas and concepts more. So we're gonna be having follow-up workshops where we go into more code if you're interested in that stuff. So I apologize in advance if y'all wanted to do that today. All right. Okay. But if y'all don't like that, then you can just leave in the feedback form and we'll probably change it back. Okay, so I'm gonna be covering a recap of the main things we learned so far. I'll just bring back this diagram if y'all are familiar. Is the basically an overview of how you train a machine learning model, and that is we have an architecture, which is trying to predict something, and we got our inputs and the parameters, and our architecture predicts something, and then we get some form of loss to tell us how wrong its prediction is, and then we update it such that the predictions get better, and we keep on doing that. So that's kind of an overview of what we covered so far. Any questions on this recap? Maybe if you weren't here, I can answer your questions real quick. Okie dokie. So to get to the meat of the workshop, what is computer vision? I have the definition right there, but anyone want to answer the question of what is computer vision or what you would think it is? Just from your understanding of stuff?
The most important aspects of an image. For example, oh, the scroll had a thick tail, so then it recognizes the tail and creates it.
Yep. Any other people want to put in their 2 cents in what computer vision is? Or if they ever saw it used somewhere, maybe you would like to mention that. What's up?
Might be kind of the difference between how a computer looks at an image and how a person looks at an image.
Yeah. So that you both kind of hit the squirrel on the head, I guess. And that is yes, we are working with computers, so the computer will have to understand the meaningful information in the photos or the images. So here, to a computer, this is completely meaningless. It doesn't have eyes. It hasn't evolved over many millions of years, and to be able to perceive things in this way. So to a computer, it doesn't see a squirrel. It just sees numbers. So what we're going to be talking about today is basically trying to get some functionality from a computer program such that it can understand the meaningful aspects of an image. So I wanted to go over just a high level, some interesting types of computer vision applications. So one I'm sure you're all familiar with because we did cover in the previous workshop is classification. And that's where you have an image and then you basically categorize it into a couple of categories, like if there's a cat present in the picture, and And another type is object detection, which detects where in the image a object, I guess in this case, a dog is in the image. So it's like kind of a combination of classification and maybe I should have removed the localization. But yes, classification and other type of task combined. So another cool thing you can do with computer vision is pose estimation. It's probably where you see all those like cool like looking videos of people having like little stick figures on them and they're like running or playing some sport or dancing. That's pose estimation. And another one that's also pretty cool. I would like to think the most cool stuff is the video stuff is event detection. So just play this quick video for y'all. So it's gonna be like detecting events in like security videos. You can just kind of see what's happening. They're like fighting at the left, and like it's tracking people moving. Like on the left, if you see, there's like little dots following people. So to us, this seems like a pretty simple task. When you just look at things, you kind of understand where it's gonna move. But for a computer, it just sees different frames, and none of it really means anything to it. So that's what we're trying to do with computer vision. Try to get some meaning behind like what's happening in these uh, number-filled matrices. Okay. So an important thing to cover first is how do computers actually view an image? So the main way a computer views an image is that it's like encoded into a matrix of numbers. So the way it's encoded in this example is there is a matrix which is one is in the x direction. One is in the x direction, and the other is in the y direction, and it's encoding the gray, like the black and white values. So 0 being white and 255 being black, and you can kind of see in this image that it's like the top half of a 3, and that's kind of how an image is kind of represented to a computer. So if you just imagine seeing these numbers over here on the left on the whiteboard, do you have an idea of what this image looks like? So in a sense, the computer kind of has that same feeling if I were to like make it into a human. It just sees this and it's like, I don't know what this means. So that's kind of to bring back the idea of how computers don't really understand it because they just don't have enough information. And another way computers like kind of encode images is they have different channels for different colors, and then they're kind of layered on top of each other. So you get like a full colored image. So on the left, we kind of see different numbers, and then similar to what we saw in the last slide, a matrix with numbers, but now we just stack them on top of each other. So it'd be red, green, and blue. If you're familiar with RGB, like the three main primary colors, I guess, I think. I'm not an arts major, so don't quote me on that. So like, how do images differ from what we worked with before? Just any answers? Like, just raise your hand. So before we had like 3 features, like the size of the house, the age of the house. Like, what's different from that in an image? Just like say obvious stuff if you want to.
Like different colors between different images, different sizes between different images.
Yeah, so like those are the main things, like different colors, different sizes, and also they are much larger. So before we only had like 3 like input values, which was 3 numbers, in like images that we have nowadays, where YouTube videos can be like 14,000 pixels by 14,000. That's like an an insanely large number of pixels. And when you feed that through a neural network, it's going to have a lot of parameters. So to bring it back to where we kind of were before, which was a simple neural network where we have on the left, where we have input values, they get multiplied by some weight values, and we get an output value. So to bring it back to that, before we had an input like vector or just inputs, but those were like basically known when you made the neural network. But with images, you kind of, as he mentioned, you can have different sizes of images. So you can't necessarily know if your image is going to be 1400 by 1400 or is it going to be 20 by 30 pixels. So we kind of have to address these limitations. So before I go into the next slide, anyone has an idea of how you can address them? It can be very simple. Like it could even be like a Band-Aid if you want.
Just the overall shape.
Huh?
Maybe an overall shape.
Sorry, what?
Overall shape, maybe.
So you're saying we can constrain the shape? Yep, that's actually one solution to the problem. And that was used for a while. Any other ideas? What's up? Okay, similar to what he said, instead of like cropping the shape, you can add padding to make it a standardized shape. That will also work. All right, so that addresses the shape difference of images, but there's also another issue we have, and that is the amount of pixels in the image. So if we fed in every input value as a pixel, there's gonna be like 100,000 like input values and 100,000 weights for each like image. So there's like a parameter explosion. Like the bigger size images you want to process, the more amount of parameters you're gonna need. Therefore, like the longer it's gonna take.
So would you make like groupings of pixels then?
Exactly. So next slide. We have little groupings of pictures and little groupings of weights. So instead of having one weight per pixel, we're gonna have a group of weights to multiply across the image. And we get our new like feature or the output matrix. So when I was introduced to this idea, just seeing like this sort of gist is good, but it wasn't like too helpful for me. So I'm gonna make y'all go through the same pain I went through, and you're gonna calculate a convolved feature matrix from a group of weights. So what I want y'all to do is like basically calculate one of the right one on this like little matrix over here. And I'll give you the feature vector. It's not gonna be too hard. So, oh, this one's kind of done. Let me know if you can't see this from over here, because it is like kind of far from y'all. Can all of y'all see this? So the top is like your image, and the bottom is your weights. So go ahead and give it a try. You should have an output matrix that looks like this. So just to summarize what's happening in this photo or this graphic is you're multiplying each of these groups of pixels by a 3x3 weight matrix in this one, and you're adding them together, and then that's how you're getting these values. So I want y'all to basically do that with this weight matrix. So I would multiply this first half by this weight and then add them all up. And I'll put it over here. So I'm gonna give y'all a couple of minutes to figure that out, and I'll come around to help y'all if you have any questions. Alright, so you want to take that small matrix over there, and first multiply by the first one.
So imagine that.
So
So the 5x5.
So this is that one. It's gonna multiply by the
It's like cross.
yes.
So you
zero
just
can
multiply
multiply
by
by
2,
9.
like the top
And then
left,
one multiply by 3.
then you multiply that with half.
So like kind of think of it like
Top
that.
left,
You see that
2
kid?
by 200 would be.
So it's kind of multiplying those. Like so, it's kind of composing it on and multiplying it.
Yeah.
Yes, yes. So it's like you imagine that
That's 2
square.
by 2 grid.
And then
or like
35
yeah. So each one fits into one of the like the box on it.
I see.
That's why I want y'all to go through the okay. So that's kind of the way it makes. So you see the smaller one I made there.
Scaling this up.
So I'm gonna go more into why this works in a bit. But the idea is that we have these weight matrices instead of before we had just like a bunch of weights for each pixel. We're kind of making it into a smaller group, so we can have we can use it on different image sizes, and it's not as many weights. I'll go more into it.
Yeah.
But you just try to calculate that.
Turn a single pixel each 5 times.
Yeah, you just keep doing multiplication and addition. And you're gonna try to do it like being done in that picture, but with that matrix. I'm gonna go over it. Good. Yeah. We'll check the answers. Sorry. It's like these ones here. Yes.
No.
So it's say like yes, there, and this is gonna be like less than time. Because before you do like maybe a policy multiplication, you might have to do this one.
Yeah, that makes sense.
So I'll go more into that.
There's no.
I'll go more into here.
Yeah. He's probably in his late 70s or 80s. Wisdom somewhere not increasing.
All right. I'm gonna go over this problem and kind of explain it as I go. So it's nice that I saw that y'all were figuring it out, and you also had some interesting questions. And I'll go through both of those right now. So to basically summarize the idea, we're taking this matrix and basically throwing it on top of that and multiplying them together. And then we're moving it over one step, moving it down, and then the other direction, basically. And then we get this like output matrix or convolved features as it says there. So I'm gonna just go over that with y'all so you guys know how it works. So I'm basically multiplying 1 times 100, that's 100. Multiplying 0 times 75, that's 0. 0 times 100, that's 0. 1 times 50, that's 50. And then we add them up, so it'd be 150. Okay. And then similarly, I'm gonna just go through it quickly. But 1 times 75, multiply 100 by 0, that's 0. 1 times 25, that's 25. And then 50 times 0. And then we sum it up, that's 100. And similarly, I'll just go through it. 200, 1 times 100, 50 times 0, 35 times 0, 1 times 100, and sum it up. Similarly, 1 times 50, 50, 1 times 50 is also 50, so that'll be 100. So if y'all got this answer, that should be correct. Any questions about the process of how we got this answer? Or if y'all didn't follow along with how it works, or you got an incorrect answer? All right, just raise your hand if you got this answer correct. All right, cool. That's nice. All right. So to answer some questions some of y'all had, which was why are we, where are the, like, what are the weights? And like, how are they changing when we do this? So basically to answer that, in this GIF, we got the weights up. It's moving, but it's the red things in the corners, and they're multiplied against the image. So how this works is that instead of having, let's say, instead of having 25 parameters, we only have to have 9. Because there's 25 pixels in this image, we only have to have 9. So let's say the image was instead of 124 pixels, we'll only have to have 9 again. So that's one benefit of using this weighted matrix as the weights. And another thing is how would we update these? So just like we updated the weights before, where we had our little weight vectors where we multiplied it by the input values, which was weight times x, we kind of have the same situation here, but we're just multiplying in a different way. So just like before where we had the slope of the loss, the same thing applies here, where we can get the slope of this weighted feature vector, or a matrix, sorry, this weighted feature matrix, and we can change them accordingly just like we did before. The only difference is that it's able to handle different size images, and it saves us a lot of parameters that we probably wouldn't have needed before. So another thing to look at here is kind of how you can visualize what these features mean, and that is like let me show you an example here. So let's say I multiply this feature vector over here. You can kind of see that it would be looking for diagonal edges, because the ones on the edge, like the one at the top left and the one in the bottom right is a 1, and then the other ones are 0. So it's clearly not keeping the information there if it's on this side. So if you multiply them together, you'll see that these types of edges will have higher values. And with that, you can kind of see like in this corner, the 150, they have higher values than this 75 and 25. And to kind of show you how what that kind of means is like, let's say in this image, I had the same thing where I was detecting this diagonal edge like this. I can kind of see this is a higher value than the 0, 0. So it's kind of detecting different features on the images, but with numbers. So in the last workshop, I showed you an image of an example of what features could look like, and this is like an actual usage of it. So, okay. And the main thing you'll face when designing these sorts of, go ahead.
If the size of our image pre-convolution is n and the matrix that we're covering with by is k, then will the convolved feature always have a size of n minus k plus 1?
Yep. So there's actually something we can do to combat that, and I was about to go into that in the next slide. So no, it's all good. So when we're designing these sorts of things, you can see how the size of the outputs changed from the inputs. So like the main thing we would face when designing these convolutional neural networks, as they are called, is that we just have to figure out how the sizes of each thing should be. That's kind of the hardest part when you're actually implementing it, when you're creating the network. So to get the idea is, the main image here is like 224, I guess, by 224. And then we have to progressively make them smaller to get like maybe one classification value. So the whole like deal with designing these networks is that we have to make them smaller in a way that they kind of get to the size we want. So there's a couple of things, there's a couple of tools we have for that. And one is padding the images. So as we saw before, the features, the size of the features, they get smaller. So what we can do is just add some padding around it. And it will either keep the same size or it might increase depending on your convolution size. And another thing we can do, it's called pooling. And that is where we either take the max of a region and we get it into a smaller thing, or we can take the average of a region and we can do it into a smaller thing. So the reasoning why we do this is just to change the size of the features. So any questions so far? I know this might be a bit of a jump. What's up?
In both cases, what if we have like a really high outlier?
A high outlier, what do you mean by that?
Like one of the boxes has a really high value, but the other ones are really small.
So that means it's working exactly as expected because it's detecting those things.
Oh, okay. Right.
Because in like an image, they might have zeros in a majority of the places, but where there actually are things, they might have higher values. So if there are higher values in this, we are kind of doing what we're supposed to do. So go ahead.
Different question. Like, what would be like a real life application?
Yeah. So yeah, I'll be going into that a bit later. But to answer your question, similar to how we structured our machine learning before, where we had labels and we had our weights, and then we updated the weights, we're going to do the same thing, but now we have something that can take in inputs that are of different sizes. And we have something that doesn't need like a million parameters for a 1400 by 1400 image. So those are the two benefits of using this. There are other ones, but I won't go into that right now. So any other questions before we proceed? All right, to get this idea down, I want y'all to also go through this with this image. So I want y'all to try doing max pooling and average pooling. And why we're gonna have y'all do this is when you're designing these convolutional neural networks, it is kind of hard to understand like what these things actually like feel like until you actually do it. So that's why I'm having y'all actually do this on paper. So go ahead and do this on this middle image right here. I'm gonna erase this so it doesn't confuse you. And I'm gonna do the same thing where I go around. And raise your hand if you have any questions. I'll come to you. Oh yeah. So to answer a question he just asked, we want it to be a 2x2 shape. So I'm gonna have a similar thing here. So just pull like 4 at a time, I guess. Okey-dokey. And I want y'all to do both max and average, by the way. Yeah, that's so in this example, but when the model so it's but it's good that you know stuff. I should choose each. Well, yeah, feel free to use a calculator if you want.
Yeah, I don't know.
I should remember that.
So you say divided by 3. I don't know.
And plus 2. Yeah.
I did divided by 2. Yeah, 7.
Yeah, exactly. But yeah, that's okay. Yeah, we had to. So how it works is retain the sex theory classes. Yeah. So we use that allows you to detect different features, maybe another one that allows another way to learn other methods, and the other one can just and
Yeah.
now we have to find out for second one out of this one. So basically, just give it a bunch of different features, like even each one is a different feature. And it gives them more capabilities to learn more complex shape understanding of it. So different feature, yeah, I hope that so right now, yeah, is I mean, everyone searches on the image. Oh, so it's rated I would train it but right here, what we're doing is trying to change the size of the image to small. And we're doing it as particular maps of square. And smaller or small features. And yes, relative are it was sorry. But yeah, that's it. Where we're seeing small regions and the max value for small region. And then the other small region, so just slow and trying to see what's the
Yeah. I think that's gonna be, you can take the course.
And there's another one. Yeah. All right, so I'm gonna continue. So I had a nice conversation with someone who had asked some questions, and I wanted to go over that with y'all also, so you can kind of have an understanding. So going back to where I kind of went over like having, can y'all quiet down, please? Having a feature vector for the convolutions or the weight matrix, where I had one that can kind of detect diagonal stuff. So to kind of motivate this idea a bit more, this matrix I'm showing you right here, it was hand designed by people over many years. It looks pretty simple, but before every use of machine learning or like neural networks, there was someone doing it by hand and coming up with these weights, feature matrices by themselves. So just think a group of computer vision specialists coming up with like this sort of feature weight matrix. And they found that this was useful for detecting edges. And basically, what the neural network is doing, it's kind of learning its own weight matrix that is good for the task. So instead of having to hand make these weight matrices, we have our neural network kind of learning over optimizing like on the task, like what's the best features for this task? Do I need to have a diagonal line detector? Do I need to have a straight line detector? Well, I wouldn't know. I'm not a computer vision specialist, but the neural network will basically automatically learn good features for your task. And another thing to add on top of that is that we might want to detect more than one feature at a time. So here we have a diagonal matrix. We might want to have a straight line matrix, make it a 9 by 9. So it would be 0, 0, 0, 1, 1, 1. So I might want to detect where there are straight lines. I might also want to detect where there are vertical lines. So what we also do is we have multiple weight matrices stacked on top of each other, so it can detect more than just like a diagonal line. Like when you see a dog, there's more than just diagonal lines. So it's very useful for them to detect not only diagonals, horizontal lines, vertical lines. That's kind of the idea there is. But the model itself might learn something completely different that might not be as simple as a line. But that's the beauty of the model. It learns stuff that we couldn't have done by hand. So that's kind of to go more in depth into like the motivation behind this stuff. Thanks to the person in the back who brought that up. Okay.
Thank you.
Oh yeah, back to the question. All right, this one. I'm gonna just go through the max pooling because we are a bit short on time. So here we look in this region and we find the maximum value is gonna be 100. So 100's bigger than 75 and 50, so that's why it's 100. And then we go ahead and do that in the next region, and then that's also gonna be 100. And doing the next region, also 100. And then again, it's also 100. So let's see. To bring it back to the main idea, we went over a different architecture to more easily handle images that are big and are of different sizes. The convolutions allow us to get outputs that can work on different size images, and they don't require a million or a billion parameters for a simple image. So what is left? We showed you examples of different computer vision techniques. So how can we do these cool tasks? So all I've shown you so far is a nice architecture to make our job a bit easier. But how can we classify the images? How can we detect where in the image an object is? And how can we estimate the pose of a person or an object or an animal or a moving figure in the right or the left? So what we can do is we can change the labels. So in the architecture, we have a nice way of predicting on different images. Now, when you take the prediction and train it with like examples of answers on the tasks we want. So any ideas on how we can choose good output values that would give us like this square box maybe? Just raise your hand if you have an idea. So we want to basically draw this square box. What do we need for the model to output for that?
X and Y for it to, four points of X and Y to determine where the box is going to be.
Exactly. Yeah. So we would run our model to output the box around the object. And then if we combine this object detection task, we would also want to output the class of the object. So we would have two things, a vector showing where the image is. So it would have the x, y coordinates of this left vertex, this one, and this one, and this one. And our little computer vision like image thingy, we can just draw that little square or rectangle around the object. So again, it might be similar. How would we get this nice looking skeleton or like this pose estimation? Any ideas?
You just find the XY coordinates of each of the points in different like joints, and then you just connect them.
Exactly. So you kind of see a common theme here. Instead of just classifying in the image, we're also drawing like little vectors. We're getting the coordinates of where the objects are in the image. And another idea, how would we do it in a video? Let me just speed it up a little to where it's showing stuff. So how would we do it in this like image where we have it following along?
You just grab the coordinates for each frame.
Exactly. So what we want to do is instead of just having let's just give a circle as an example. Let me just pause this. Instead of just having a circle, we can have this like coordinate value. Let's say it's 0.2 or 0.5 and 1, and that's like where the dude is. So I will have this for each frame in the video. So I just have another array. And then similarly, I would be like 1, 2, and then it will just continue so on for each frame in the video. So I would basically be feeding in the images, and then it'll be producing the different values, and I'll just stack them together. Okay. So the main idea here is for the different computer vision tasks, we need to add different labels. Because it's a different task, we have different things we want from it. So as I said, we would have to find the location of the box here as an example. And then similarly, the category, cat and dog. And lastly, we do this for every frame for a video. So this is kind of an overview of how computer vision works. We're going to be having a follow-up workshop where we go in depth with code and implement this stuff with code. So that's going to be a follow-up workshop we're going to be having. We'll tell you when we have it. But that's like the main idea we got through here. We got through a different architecture, and we got through how do we deal with different tasks. Any questions about how we deal with different tasks? So I know it might not seem that complicated, but it really is this simple. You just change the labels, and you just get a different, with the same model, you can get a different like answer, I guess. And lastly, we're gonna be having our sign-in feedback form. So I want y'all to like talk about how we did stuff today. So if it was a good thing that we kind of showed examples and went through like that, just say I like that, and I will probably do that for the next application ones also. And the right form is the sign-in form, or the left one, sorry. And the sign-in code is right below it, so for the people who can't see, I'll write it on the board. What's up?
The sign form is this option available again.
All right, give us a couple of minutes on the sign-in form. Apparently it says no options are available. But yeah, you can fill out the feedback form in the meantime and tell me how we keep on messing up the sign-in form. I'm gonna just write down the code so when we do get it back up, you can type it in. All right, so in the meantime, do y'all have any questions? It doesn't have to be particularly about this workshop, maybe about future stuff. Just raise your hand and I'll answer them. What's up? So what we're thinking about doing is we're gonna have ML Monday say more like kind of like showing you how different AI applications work. Since like coding can be a bit tedious to follow along with, we're gonna have that into a different workshop, and we can go more into like different types of applications in ML Mondays. But yeah, it's gonna be like a follow-up workshop. It's still we still have to determine when those are gonna be, but we'll let you know sometime this week. Maybe I have a question for y'all. How are you enjoying it so far? Any like advice on how we should keep on doing things or what we should try differently? All right. It should be working? Have y'all been able to sign into the sign-in form? Just raise your hand if you were. All right, the president low-key is gonna help y'all out. He's gonna figure it out. So sign. Yeah, I'll send in the.
Wait, is it not taking to? Wait, can you even access a link?
Huh.
Okay, so
Can you just send me the link?
yeah.
Actually, send in resources. Oh yeah, so for the next workshop, I think we're going to be doing natural language processing. So I wanted to get like a group of people or hand count for how many people want like after that introductory NLP like workshop. How many of y'all want to like go more into LLMs, where we show y'all how to use an API to basically do stuff with LLMs? Like just get a raise of hands for how many of y'all want that after the introductory NLP one. All right, seems like it's a majority of people here. All right, I'll keep that in mind. So I'll probably have a workshop after the first NLP one, where we go more in depth into actually using large language models and maybe going over some of the misconceptions people have about how they're trained and what you can do with them. So the attendance link should be on the Discord. It's on the AIS resources tab. I'm gonna put it up on the PowerPoint real quick. Oh, okay. So it's right here. I'm gonna just make a QR code real quick for it. Yes. Yeah. Maybe try this QR code. I think it might have been a QR code issue. And there's a link for it below if you can't get the QR code. Oh, sorry. Okay. Maybe it went stale or something. I'm gonna go off live.
Like,